Okay, we have a rechargeable car here being charged by a recharger thing. The car's battery is 330 volts. It can store 64 megajoules of energy, so that's like the petrol capacity of a normal car, okay? It's like the fuel tank. It can store 64 million joules of energy. It takes 8 hours to charge, and we have to work out the total charge. In fact, they say the exact wording is calculate the total charge that flows when the battery is being charged. Okay, I don't really like the wording they've used in the question. They want you to work out the total charge that has flowed from the point it starts charging to when it's full. Okay, work out the total charge. The way they've worded it, work out the total charge that flows. Edexcel, listen, you shouldn't really use wording like that because it makes it sound like you have to calculate the current, okay? But you don't. Calculate the total charge that flows while the battery is being charged. Again, while the battery is being charged, it makes it sound like current. Make it clear in the question that you're asking for the total charge, okay? All right. So we have to work out total charge, Q, not I. Right, so the quick way to do this is to use the equation that energy is charge times voltage, okay? Did you know that equation? If you didn't, learn it now. It can come in very handy, right? Energy is charge times voltage. So rearrange, therefore Q is equal to E over V. Energy, total energy stored is that, we've got that. We know the voltage of the battery that's being recharged. So we've got E and V, and that's it. We can work out the total charge that will have flowed to fill up that battery. To recharge the battery is a better way of putting it. Okay? So we don't actually need to know that. That's a bit of a red herring in a sense. Okay? So let's put in the numbers. E, energy, 64 megajoules. So don't forget that M there, that's important. Okay, it's not just 64. It's not kilo either, it's mega, which means 6 noughts. Over the voltage, which is 330. Okay, stick that in your calculator and you get 193939.3939. Okay, it's charged, so the unit is coulombs, C. We're not going to leave it like that. Make a sensible choice. 3 significant figures is sensible. That 9 pushes that 3 up to a 4. 194000 coulombs to 3 significant figures. I think 2 significant figures would also be fine. You could say 190000, okay? But that's fine. 3SF is a sensible choice, okay? As long as you make a sensible choice, you won't lose marks, it'll be fine. Okay, good, right. So that's the best way to do this question. The fact they tell you that it takes 8 hours to charge, you can use that in a roundabout sort of way. If you didn't know this equation, and like I say, learn it right now, it's very useful, E is QV, then you can go down the route of using energy is power, or power is energy per unit time, and power is V times I, and then Q is I over T. Right, I'll show you what I'm talking about. So, right, firstly, let me say where this equation comes from. You kind of notice from looking at units, voltage, okay, voltage is, or one volt is 1 joule per coulomb. Okay, so just looking at the units, a volt is a joule per coulomb. If we rearrange that equation, we get V is E over Q. E over Q, okay? Look at that. Energy, joules, charge, coulombs. So you can work that out just from knowing the units of voltage, okay? Anyway, right, I'll show you how, if you didn't know that equation, you could also do this question. So we have total energy, and energy is, or rather power, let's do it from the perspective of power, yeah. Power is the rate of energy, or energy divided by time, okay? And this is where the time, the 8 hours, will come in, right? Also, power is voltage times current. So that's where the voltage comes in, okay? And the current is the charge divided by time, okay? Charge is what we want, time is 8 hours. So let's sub in and rearrange these 3 equations, and we'll actually get that one out. So like I say, this is just a bit of extra information if you didn't know that equation and you wanted, if you knew these equations. I think these are probably more familiar to you than this one. I'm just showing you how, we've already done the question, that's the best way to do it. I'm just showing you how you could do it using these equations. Okay, so we want Q. So let's rearrange this. Q is I times T. Right. I is P over V. Okay, so sub that in there. Therefore, Q is PT over V. Let's check that. Q is P over V times T. Correct. Okay. Now, we don't know the power, but we do know the total energy, so we're going to use this. So from up here, we know that, oh yeah, we just sub power into there. Okay, so therefore Q is, power is E over T, so that's E over T, that's power, times T over V, times T over V. Oh, look at that. The T's cancel and we've actually got the same equation. Therefore Q is E over V. Okay? So, what you could do from these 3 equations is, you've been given the time, okay, you've been given the energy, so that's time, that's energy, and that's, looks like a T, and that's voltage. You could work out the power from E and T, from these 2, okay, you can get the power. And then you've been given the voltage, so from that and power and voltage, you could get the current, right? And then by calculating the current, you know the time, it's 8 hours, you could work out the charge. So that's fine, it'll take you a lot longer and you still get the correct answer, but you would be using the time twice unnecessarily and it would cancel. Okay, let's leave it there. So, right, next bit. Calculate the average charging current. Oh, well, that's going to be pretty easy. Where should I do it? I'll do it here, in a different colour. Right, so it wants the average charging current. So it wants current, and current is the charge per unit time. Okay? Well, we've worked out the charge and the time is 8 hours. Pretty straightforward. So that's equal to the charge. Now which of these values should we use? I'd recommend using the accurate one because that gives you the accurate answer for the current. Okay? So it's a good idea, a good habit to get into, to when you get the accurate number there, put that in the memory in your calculator so you can dig it out straight away. So dig that out of your calculator. So charge is 193939.3939 divided by time. Now time has to be in seconds. What's 8 hours in seconds? Well, it's 8 hours times 60, that puts it into minutes, times 60 again. Now it's in seconds. Okay? So stick that in your calculator and it turns out to be 6.734 something something something, which is sensible choice again. One decimal place, 2 significant figures. So it's 6.7, this is current, amps to 1 dp. Okay? Happy with that? Good. Now, it's also okay, you will still get the full marks if you had chosen that value there, the rounded value, to put into this equation. Right? You still get the full marks, that's okay. And in fact, if you use 194000, you still, after rounding to 1 dp, you still get 6.7 amps. Now, if you had chosen 2 significant figures here and got 190000 and put that in here, you would have got, after rounding to 1 dp, you would have got 6.6 amps, which is obviously different, 6.7. That's okay, you'll still get full marks, right? But like I say, I would recommend, you're a scientist, you're trying to be accurate, right? So you should use the accurate value wherever you can of things you've worked out, the charge. Okay, let's move on. So, next bit. The battery charger is connected to the 230 volt AC domestic mains supply. Okay, so what they're saying is that this thing itself, behind the scenes somewhere underneath, is connected to the 230 volts AC domestic supply that we have in our houses. Okay? The output voltage of the charger is 335 volts. Okay, so this is outputting 335 volts. And it provides DC charging current. This is 335 volts DC. Charging stops if the charging current exceeds 15 amps. Okay, so 15 amps, greater than that, and it's cut. Explain how electrical components in the charger can be connected together to give this type of output. Right, what the question is asking is, you've got 230 volts going into this charging thing, and it's 230 volts AC, and it's knocking out 335 volts DC. So what's going on in between here, from there to there? We have to describe the electrical circuitry and components between there and there. Okay? 6 marks. Right, so the question is asking, how do you convert 230 volts AC into 335 volts DC? That's the question. 6 marks. Right. So, what we've got is 230 volts AC input here, okay? And somewhere over, after doing a bunch of clever electrical stuff, we're knocking out 335 volts. Let's write it in now, why not? We want an output of 335 volts DC, and that's connected to the battery in the car. Okay, so that's our output. Right, so we've got to describe and get 6 marks of what goes on in between. So, first thing, it's going from 230 volts to 335 volts. How do you convert, how do you increase voltage? Well, you need a transformer, okay? So, good, shut up. Right, let's go. To convert 230 volts to 335 volts, you need a transformer, okay? So, how do transformers work? You have a primary coil, okay? And you have an iron core, which is wrapped around. Okay? And you have I'll try and draw this one a bit more, slightly more accurately than the primary coil. And you have a secondary coil, okay? So that's our iron core. Right. So, transformers inside are pretty simple. It's just an iron core with one primary coil, the input wrapped around it, and another coil, the output wrapped around on the other side. And these two coils are not physically connected. And they're not in electrical contact with the core either. It's insulated. Okay, so current can't just flow in here, flow through the core, then out to the secondary coil. Okay, so a transformer will convert 230 volts AC into, now the output there will be 335 volts, 335 volts. It'll still be AC, okay? AC. Right, good. Now, how do we convert AC into DC? Well, that's what we're going to do here. You can do it very easily with just one diode, okay? So, quite simply, if you just stick in a diode there, right, you now have 335 volts DC output, okay? Simple as that. Alternating current means the current is going one way, then the other, one way, then the other. But if you put in just one diode, okay, it can't go in that direction like that. It can only go like that. So the AC will be going like that, then it won't do anything. It'll go like that, then nothing, then that. So it's converted into DC. Right? So that's fine for an answer. What you could also say is use an AC-DC converter, right? Stick one of those in. So that's an AC-DC converter. And that will output your 335 DC. What is an AC-DC converter? Okay, you don't need to know exactly how they work inside, right? But it's actually not that complicated. Now, remember, you don't need to know this for your exams. This is just a little bit of extra information. It's an arrangement of 4 diodes inside, okay? And you could mention that. There's nothing wrong with saying a little bit more than what you technically need to know. Okay, nothing wrong with knowing more than you need to know generally, right? So you could say that an AC-DC converter has an arrangement of 4 diodes inside, and that will convert from 335 AC to DC. Something like that in your exam answer, okay? Right, so I'll move on now because, like I say, you don't need to know the internal workings of an AC-DC converter, but I am going to talk about that at the end just for general interest. I'll show you how the 4 diodes are arranged and how it works. It's not that difficult. Okay, next we have our 335 volts DC. Good, which is what we want. The final thing we have to cover is the circuit breaks if the current goes above 15 amps. How do we do that? Well, the simple way would be just a fuse, right? 15 amp fuse. That's pretty simple. That would work, okay? When the current goes above 15 amps, the fuse melts and it breaks the circuit, right? So that would be fine. There we go. We have converted our 230 volts AC into 335 volts DC with 15 amp fuse. Brilliant. But again, I think there's a slightly better way of doing it than a 15 amp fuse. And that would be to use let's do a different color, a circuit breaker. Okay? Now, again, you definitely don't need to know how a circuit breaker works internally at this level, right? You just need to know that they sense the current going in and out, and whenever it goes above 15 amps, it will shut the current off, okay? I think that's a preferable solution to a fuse because the circuit breaker is resettable. Okay, as soon as you can have ones where as soon as the current falls below 15 amps, it will automatically reset and everything will be fine. Or someone can come along and flick a switch and reset it, much like the circuit breakers in your house. Okay, so there we are. That's it. Everything I've said there will get you the full 6 marks. Okay, so we've finished the question, okay? We've got our 6 marks for this one, we've done the whole thing, brilliant. Now, I did say I wanted to talk more about how an AC-DC converter works. So, let's do that now. I do want to stress, this is a bit of extra on top, okay? Just for interest and for fun, okay? Now, this is an Edexcel exam, and I've checked the Edexcel syllabus, the 9-to-1 physics syllabus, and you don't need to know how a AC-DC converter works inside, okay? You do need to know that a single diode there would also do the job, but so you need to know how a single diode works, but what I'm going to do now, you don't need to know this for your 9-to-1 exam. Anyway, let's get on with it. So, what we have is a 230, well, just an AC input, doesn't matter what the voltage is, okay? And we're going to use 4 diodes in a clever arrangement to get a DC output. And it works like this. Okay, let's see if I can remember this. You draw a diamond thing like that, square, whatever. So one output there, and the other output is going to be there. Okay, so our input is between these 2 points here, and our output is between these 2 points there. So this will give us a DC output. If we have 4 diodes arranged like this, so one there, one there, one there, and one there. Right, there we go. So, how does this work? Well, this is AC, so let's consider the case when that is positive and that's negative. All right, so current is able to flow along here. It can't go down there, but it can go through the diode in that direction, and it can flow like so. Okay, so a positive voltage there will result in a positive voltage there, because current can flow like that. And current can flow in the opposite direction. In this direction, it can go through that diode. Yes, it can go through that diode, but it's not going to join up and join that current because there's nothing driving that, okay? It would flow in this loop here, okay? Good. Now, this AC current is going to, let's do this in blue, it's going to switch around in a second, right? Because it's AC, positive, negative 1 second, then switches, negative, positive the other, alternating current. So, what happens when this is negative and that's positive? So, current wants to flow in this direction, like so. Can't go past that diode, but it can go through that one. And, oh look, it will end up at the same point. Now, what about negative? So current will want to flow like that, and it can do because it can flow like that. It's not going to do that. It can go through that diode there, okay, and along there like so. And that's it. Does that make sense? So with this arrangement of diodes, no matter how you arrange the positive or negative voltage here, you always get a positive voltage there and a negative one there. Okay, let's just finish that off. So negative and it's going to be positive, negative, like so. Boom! There you go. So that is an AC-DC converter. Also known, this particular arrangement is a full wave rectifier, because when the input voltage is like this, okay, so that's input, the output voltage will be like so. Okay, that is a full wave rectifier, and that's this. Okay, so full wave. It's probably hyphenated. Full wave rectifier. The single diode arrangement, which would also convert AC to DC, that is a half wave rectifier, because for an input like this, the output will be like that. Okay, so again, that's output and input. This is a half wave rectifier. Because if that's just connected up there and you've got it's just a single diode in there, it allows current to flow in one direction, but when it tries to flow in the other, it just blocks it dead. So the full wave rectifier is just a bit more clever. You always get output no matter what the input. Good. Right. So I could have drawn in here. Let's see. If you want, you can put in the, so that would be to there. You can put in the arrangement of diodes in your exam. Right, the output, that goes to there. That one goes to there. The diodes be like so. Okay, so there you go. So yeah, I mean, in your exam, there's nothing wrong with drawing the actual arrangement of 4 diodes if you can remember it. But like I say, you don't need to know that for Edexcel 9 to 1. But I hope you found that interesting anyway. So there you go. That is a full wave rectifier AC DC converter. Just 4 diodes.